Okay, this is another application of the law of induction. So the Faraday's law tells us that the induced EMF is equal to the negative um, rate of change of the magnetic flux through a loop. So in this circuit, we are given, well, actually, in this problem, we are given two circuits. This is a very famous problem, well known. So where you have a conductor, capacitor that is already charged, and this capacitor will start discharging through this resistor. And when we close the switch, of course, because the capacitor is being discharged, the electric current will change as a function of as a function of the time, which means the magnetic field inside this loop, even though if the loop area is fixed, is constant, but the flux is changing because the electric field, the electric current is changing, and the magnetic field will be, of course, changing as a function of time. Now, there are two circuits. The circuit to the left, which is a normal discharging capacitor, which we already saw. I will not cover it. So all what I will give is you can consult previous videos about capacitors and RC circuit, but for the moment, the charge as a function of time is equal to the initial charge exponential minus t, the time constant, and then the time constant is equal to R0C. R0 is given, C is given, and then this is the time constant, and then Q0, we know that Q0 is equal to this is the total charge on the capacitor at the beginning, and we know that the capacitor has been charged previously through 100 volt. Okay, so this means that the total charge will be equal to charge times the voltage, which will be 20 10 to the minus 6 times 100 volt. So this is the charge initially at the capacitor, and you can also that the current, which is equal to minus dq over dt, is equal to q0 over rc exponential minus t over rc. Okay, so this is the changing current as the capacitor is being discharged. And you can see that here we have a current that is changing as a function of time. Now you can, of course, you can use this formula to find the question answer to question A. Just replace time by 2 microseconds, and you will get the answer. Now, what is interesting for me is question B. Find the flux through the small loop due to the magnetic field created by the long wire nearest to the loop. So we'll consider only this wire because this is the most closest one. Now, let's make a drawing. So we know that, so this is a current that is given now by IT, and then we have a loop that is located at a distance c, and this loop has an A and B side, and the question is to calculate the flux through this whole area. Okay, now obviously we cannot apply directly the formula. Why? Because the distance, if you take a point here, the magnetic field created by this current in this point, I will call it X, is different than point Y because the distance is different. So this means that we have to go for the integration. So we will define a small element, R. Okay, let's define a small band, and we will calculate the magnetic flux induced or created into this. I will call the width of this is dr, which means the area. The area is equal to drb. So the magnetic flux in this small area, okay, is equal to B, and then the magnetic field, and then the B dr, magnetic field, and this is the area. Okay, well, and we know that the magnetic field created by a current at a distance r is equal to mu 0 I divided by 2 pi r, right? So the magnetic flux in this small area band, small band, is equal to mu 0 I over 2 pi r b dr, which I can arrange as mu 0 I b 2 pi dr over r. Okay. Now, if I want to calculate the total magnetic flux, of course, I have to integrate, and the integration over the full area. Well, from here to here, over the full length, which means from C to C plus A, because this point is at C and this point is C plus A, and then the small dB, which is 2 pi dr over r, right? Mu 0 I b 2 pi. So all these quantities are constant as a function of space. So I can get them out of the integral, and obviously you can easily check that this will give you ln of C plus A over C. So this is the magnetic flux. Now, again, the magnetic flux is equal to mu 0 B over 2 pi ln C plus A over C. All of these are constant, and then I, which is Q0, the initial charge divided by the time constant R0C, and then exponential minus T over tau. Well, tau is equal to R0C. So all of this is constant, and now we can calculate the induced EMF, because now we have a flux that is changing as a function of time. So the induced EMF is equal to minus this. Of course, everything here is constant. It will give me minus, and then mu 0 B over 2 pi ln C plus A over C, Q0 over R0C. But then I have minus 1 over R0C exponential minus T over R0C. So this is negative, this is negative, it gives me a positive EMF. So the EMF will be mu 0 B over 2 pi ln C plus A over C, Q0 over R0C squared exponential minus T over 0C. Now this is EMF that is positive. You can see that this means that it will be anti-clockwise. The direction will be anti-clockwise. So this is question B. Now question B, C, find the electromotive force induced in the small loop as well as the current flowing through it 200 microsecond after S, so 200 microsecond. Well, all what you have to do is to calculate this. So you have the time, you can calculate everything, and you can also calculate the current. Now, how do you calculate the current? How do you calculate the current? You have the resistance. You have, so let's calculate. So at T 200 microsecond, so we can calculate E. Just, I did not do the calculation, but you can calculate it. You have everything. Now, how do I calculate the current induced in the loop? Well, I know that the current will be the EMF divided by the resistance of the loop. And the resistance of the loop is given. So we can calculate the resistance of the loop. So we know that the loop has, this is A, this is B, this is 10 centimeters, this is 20 centimeters, and it has 1 ohm per meter, so the wire. And then it has 25 loops. This means that the resistance will be, the first thing is that we need to find the length. The length will be the perimeters times 2 times 25, which will give you 0.1 plus 0.2 plus 25. This 50 times, so it will give you 15 meters. Okay, and we know that 15 in each meter there is 1 ohm. This means that the resistance is 15 ohm. So which you can now calculate the inside the loop, which is equal to the EMF that you would have found before divided by 15 ohms. Okay, so this is the answer.